Good afternoon, good evening. Welcome everyone again to the TechX conference. This is the first keynote today. This is a very interesting session, and as you know, the TechX is one of our premium conferences. It's happening virtual today and tomorrow. There were a lot of exciting panels earlier today, but this session is even more special because we are going to have a keynote by our own daughter Stephen Goodnick from Arizona State University. And then we also have with us Dr. Russ Harrison from IEEE USA. On behalf of the HKN Board of Governors, I take great honor and pride in welcoming both of them. So for our audience out there, the CHIP Act is a very important topic today. And this keynote, you will hear back from these global leaders and the importance of the CHIP Act and its relevance, to your future. So without any further ado, I welcome Dr. Steve Goodnick and Dr. Russell Harrison to go ahead and deliver the keynote today. Thank you again.
Well, thank you very much, Sampath, and it's a great pleasure to be here and talk about some of this close to my heart, because I've been teaching semiconductors for over 30 years at Arizona State University. And what I wanted to do was give a little bit of background, because I know this is a general audience, and so I just want to get some context to semiconductor technology and transistors, and what is the basis for the CHIPS Act, and then talk about the CHIPS Act itself, and then talk about some of the workforce needs and issues involving workforce development in future careers in the semiconductor and microelectronics industry. So as probably most of you know, the transistor was discovered, or not discovered, but developed. Actually, it preceded Bell Labs, but Bell Labs was the first to demonstrate what was called a point contact bipolar junction transistor in 1947, and it was the group of individuals shown there that received the Nobel Prize for the development of the transistor. But since that time, over 60 years, there's just been an explosion of growth in the semiconductor industry, and these are just some benchmarks showing the growth of the industry measured in terms of the number of transistors on a chip. And so, in 1997, early on in the 50s, there was only a few transistors per chip when the first integrated circuits were made. This is a Motorola chip in 1997 that has 7 million transistors, then an Intel chip in 2012 that has 5 billion transistors, and now in 2023 we have more than 50 billion transistors per chip. And so this explosive growth is because of the development of integrated circuits. And so this is the Jack Kilby and Robert Noyce are basically credited with the development of the first integrated circuits. Even though the transistor was developed at Bell Laboratories by the group that was mentioned before, they didn't commercialize the technology. It took Texas Instruments and Jack Kilby, who received the Nobel Prize recently for this innovation, was to actually integrate semiconductor transistors onto a semiconductor platform that was the basis of making integrated circuits, in which all the different transistors that form the integrated circuit are all on the same surface, which is called a planar integrated technology. Fairchild also, which is the predecessor of Intel, also at the same time, almost the same time, developed the first IC there as well, and that was the basis of what we call Silicon Valley. So this is sort of the roots of Silicon Valley. The Bell Labs group, Shockley Labs, initially moved to California to do this startup, but quickly the engineers left and founded their own country, Fairchild Semiconductor, which is sort of the father of of Silicon Valley in a sense, father or mother, in the sense that this was the first company, and all these companies that are shown connected to this are basically descendant from Fairchild Semiconductor. First among those, of course, is Intel, but there's also AMD, National Semiconductor, and a variety of others, Cirrus Logic, Cypress, and then the companies that evolved that support the design, the EDA, you know, the electronic design automation space, and you know, companies like Xilinx, for example. In any case, you can see all the companies that came off this, and this is sort of the roots of Silicon Valley, and this is again the entrepreneurial spirit that founded Silicon Valley and led to this great growth of companies there, all around the microelectronics industry. And you know, you can then think about information technology companies as Google and everything being derived from the semiconductor industry, because it's chips that are powering all the supercomputers that are responsible for the information technology companies' success. So one of the drivers of the semiconductor industry and the rapid growth of that is something that's called Moore's Law. And this is associated with Gordon Moore, who was basically at Fairchild Semiconductor and later became a CEO at Intel. He noticed back in the 50s that the number of transistors per chip was doubling every year. And this is more like every 2 years is when it's settled into steady state. And that prediction has been actually followed closely by the semiconductor industry over many years. What's shown below here is the number of transistors per chip as a function a year going from the early 1950s, and this is a a semi-log scale. So this is starting from a few going to 50 billion up here, and this just is what you can't read. I'm sorry that the print is so small, but to fit this on the page was difficult. But these are all different processors and technologies from different companies. But you can see that this is pretty much a straight line, and that straight line is what's sometimes called Moore's Law. Although really Moore's Law is also basically the prediction that the manufacturing cost of ICs decrease at a rate that's inversely proportional to the component density. So the cost of the IC stayed approximately constant, but the density has been increasing exponentially with time, and that's really Moore's Law. And Moore's Law is a more general example of basically what's called a manufacturing curve, a manufacturing learning curve, and that is that there's a place where automation and making the same thing over and over again leads to a great reduction of cost, and you have this exponential growth. Most of these curves, manufacturing curves, if you look at other industries, have a sort of S shape. So they have this straight line behavior, and then and they start off at zero, and then they saturate at some point. And so we don't know if we've reached the end of Moore's Law or not. Some people say we've reached the end of Moore's Law, and some people say no. We're certainly reaching the limits of scaling as far as semiconductor technology, but then there's the question of what comes after that, and then there's also the innovation that's come from circuit design, and for example, the going from single cores to multi-cores, and all the innovations in computer architectures that have actually enabled this to continue. Okay. So these are just similar curves showing this case. And so what I showed before, microprocessors, this is what is dynamic random access memory. So memory in terms of the transistors per chip have gone in the same way as microprocessors. And this just shows how this has been increasing exponentially with year. And shown on the right is what's been driving that. What's been driving that has been a reduction in the dimensions of transistors with time. And what you can see is that the things like the gate length of transistors and the junction depth and the oxide thickness, these have all been going down in a sort of exponential fashion as well. At the same time, chip area has been going up, but the cost per chip has been staying the same. It's interesting to look at an analogy. And that is, if in 1970 you had a car that could go 100 miles an hour at 20 miles per gallon and cost about $20,000, and it had approximately a mass of 1,500 kilograms and this luggage capacity of 20 cubic feet. By 1995, and this is, you can continue this trend to 2023, the speed would have been 2,500,000 miles an hour. The power or the miles per gallon would have been over 1.5 million. The cost would have been $40. The mass would have been 0.06 kilograms, and the luggage capacity would be 80,000 square feet. So this is just remarkable in terms of the the evolution of the semiconductor industry. This is basically just showing that this red line down here is what I want to emphasize, is that while the number of transistors has gone up exponentially, the cost has gone down in terms of the cost per transistor. The cost per chip has stayed roughly the same at $10 for many, many years. And so that means that while the cost has stayed the same, the number of transistors has changed by over 10 to the 9th over 50 years, which is, again, the remarkable driver for the information age. This just shows semiconductor sales, and just showing a few mile marks in the in recent years. It's over a $400 billion industry, probably closer to 600 billion, and that's just the semiconductor sales. Okay, it's not. You have to think that semiconductor microchips, integrated circuits, are a enabling technology for many different technology sectors. So this is only the sales. It would be really difficult to quantify what the impact is of the sales on the technologies that it drives itself in terms of trillions of dollars. Okay, so there's been a couple of blips. So, you know, some people think of the semiconductor industry, and this is sometimes a worry for students who look at careers, has these sort of cyclical variations that you can see here. And, you know, bigger dips like during the Great Recession, there was a dot-com recession. COVID had a big impact, mostly because manufacturers, that's kind of interesting, mostly because manufacturers anticipated that there was going to be a shortage, whereas in fact there wasn't. And so there was a great shortage of chips. And we know that this led to some big bottlenecks in terms of being able to receive products. It was because the semiconductor industry anticipated that there was going to be a demand and shut down production. And so this dip by COVID is shown here. I just wanted to relate this to nanotechnology, which is something I've also worked in over many years. Nanoelectronics, I talk about as my field. Just briefly, this just shows the scale of things going from things natural and things man-made that you could see to microscopic and to then a nanoscale. Nanoscale means basically a nanometer is, of course, 10 to the minus 9th meters, but we talk about nanotechnology as roughly technologies below 100 nanometers. And the semiconductor industry has been in the nanotechnology realm for, I would say, at least 20 years. Characteristic gate lengths have been below 100 nanometers since the 2000s. And this is illustrated in this slide, which shows maybe the most important characteristic dimension that has been changing with time is what's called the gate length, which is the distance between the source and drain of a metal oxide semiconductor field effect transistor. So in 2003, this was 90 nanometers, 65, 45, 32, 22, 16. And then, you know, now we're talking about 5 nanometer, 3 nanometer, and less with current TSMC and Intel technologies. And the question is, what comes after this? Because you know, you start to run out of atoms at some point, that you can't make the distance between the source and drain more than 1 atom thick. And so there's a question of what is going to be beyond CMOS. And so we're in a realm now which is called beyond CMOS, and that's a very exciting realm from a research and development standpoint, because there really is open what is going to be the winning technologies. And now there's technology that's the hottest technology right now is called nanosheet technology, which is not even shown on here, where you have 1 nanometer thick sheets of silicon that are stacked on top of each other, making transistors in a vertical way. Vertical integration is another way that we can, you know, expand and make semiconductors even higher density by going into 3-dimensional integration. The problem is that you have a fundamental limit, which is we've actually been experiencing since the 2000s, and why chip speeds have not been increasing that fast while semiconductor dimensions have been shrinking, and that's because of heat dissipation, because as you switch transistors faster and faster, you dissipate more heat, and if you have more of them, you start to have a bottleneck in terms of thermal management. And so that's one of the limitations to going 3D, and there's another active area of research and exciting developments in controlling heat and managing heat. So let me just finish this introductory part by talking about careers in the IC industry. And there's a number of areas. One is process engineering. This is the ones maybe most closely associated with what's shown on the right here, the people in the bunny suits walking around in clean rooms. Increasingly being automated, but process engineers basically have an understanding of the whole process and are able to design the process in order to realize a certain integrated circuit technology. And so there's an enormous amount of not just knowledge of semiconductor physics, but of chemical processing, of mechanical, even construction in terms of the construction of clean rooms. So there's a lot of different disciplines, involved in process engineering. Device engineers are the ones that are responsible for what's going to come after CMOS. This is nanowire technology and tunneling, field effect technology, and carbon nanotubes. These are all different materials and possible technologies of the future. Device engineers work on that, and they have a grounding in physics and electrical engineering and materials and other disciplines. The finished devices have to be tested, and they have to be reliable. They have to last for 10 years, and so there's an equally important aspect of careers in the integrated circuit industry involving in how do you test? How do you test when you have 50 billion transistors? How do you test individual transistors? I mean, this is a crazy problem, and so this is one that the IC companies worry about, and also the reliability. Just a single cosmic ray, for example, can change the state of and destroy a transistor. You have to be able to have a redundancy built into integrated circuits such that they're immune to these kind of random failures. TCAD, technology computer-aided design and modeling, has to do with actually the computer simulation of processes and devices and how those fit into integrated circuits, how you lay those out, and how you design transistors, all using computer-aided design. And the extension of that is the EDA realm, in which you do VLSI design. How do you design actually integrated circuits with 50 billion transistors? How do you design the processors? Advanced processors are very complicated with integrated memory, cache, and everything involved with them. And of course, analog mixed signal design. So this is sort of, core careers in the integrated circuit industry, but also the other careers in semiconductors have to do with the fields of optical communication, optical devices, optoelectronics. This is a whole field in itself related more to communication technology that's driven by semiconductors in terms of the emitters of light and the detectors of light. Another area that has been growing at a similar Moore's law rate to the integrated circuit industry is solar energy, driven by photovoltaics. Photovoltaics are simply PN junction devices, the core of the integrated circuit industry, but they have been increasing in the efficiency and decreased cost in an exponential fashion, such that the cost of solar cells to manufacture now are less than 25 cents a watt. Another big area is power electronics and power devices, and power electronics is revolutionizing the electrical grid and replacing all these spinning magnetic machines with basically integrated circuits, except integrated circuits that can handle large amounts of power. So power electronics has to do with transistors and other semiconductor devices that are able to switch and manage large power, and these are what are increasingly replacing or being increasingly integrated into the power grid structure, and are responsible for amazing efficiencies, and are becoming increasingly important in terms of how you integrate these solar renewable energy technologies like radar and so forth. And they are basically semiconductors that are used at high frequencies that operates at hundreds of gigahertz. They're responsible for the evolution of communications from 4G to 5G to 6G. And so this is another big area in which semiconductors, again, play a big role, and you can have careers in all of these areas. And so I hope I've, at least given you a good idea about careers in the semiconductor area. And now I want to talk about exactly what's going on in terms of the CHIPS Act. And I'm sorry that this view graph didn't come through, but it's basically a slide deck, partly that comes from the Semiconductor Industry Association. And then it was given in a presentation by Gil Vandentop at Intel, and I borrowed it from him. This is basically talking about the CHIPS and Science Act, which was passed last summer. And this was the largest single investment by the US government into the semiconductor industry ever. And it basically was $52 billion of investment, 39 billion of which is going directly into the semiconductor industry in terms of building new facilities, manufacturing incentives, manufacturing investment tax credits, many things to basically incentivize manufacturing in the US. So the big driver, one of the big drivers was to make the semiconductor industry in the US more competitive. It was, of course, developed in the US, as I talked about the history, but over the last 20 years, increasingly manufacturing has moved offshore, particularly to Asia. The CHIPS Act is an attempt to try to revitalize that in the US in terms of the manufacturing. And that is then the motivation for this CHIPS Act, which is, again, a large amount of money, $52 billion over 5 years. Besides the 39 billion invested in manufacturing and directly in the semiconductors, 13 billion is going to basically research and development and workforce infrastructure investment. In other words, building up the semiconductor workforce, meaning training more engineers to work in the semiconductor and microelectronics industries. And that's what I'll talk about more here in the next few slides. This is just showing the ecosystem nationwide of semiconductors. It's showing the clustering in the West Coast, Arizona, Texas, New York. These are areas of high manufacturing of semiconductors with companies like Intel, but other companies too. In Arizona, of course, TSMC is building their first facility, a $40 billion investment that we have here. We're very excited about. And this is the first investment by TSMC, who's in terms of sales, the world's largest manufacturer of semiconductors, a Taiwanese company. And so this is in addition to several Intel fabs that are here already and 2 more that are being built. And then there's other areas where they're prototyping. There are government research facilities and universities as well involved in the semiconductor R&D sphere. This is how the money is being allocated. So $11 billion has been given to the Department of Commerce to invest in something called National Semiconductor Technology Centers, NSTCs, and National Advanced Packaging Manufacturing Programs. Packaging is something I failed to note in my previous few graphs, which was an omission, because the packaging is increasingly as important as the manufacture of the semiconductor chips itself, especially with all the heat problems that I mentioned before and high frequency and other things. That packaging and how you put chips together into chip holders and to basically thermally manage them and to be able to take signals on and off reliably. This is all part of packaging, and so packaging also is playing a big role in this this area. And that, again, involves skills that are important into electrical, computer, and other IEEE related areas of interest. $2 billion is going to the Department of Defense as well, and that's already been bid in terms of setting up a number of regional hubs that are going to address the defense integrated circuit needs in the US. And this is just a breakout by year of those, so I don't think, in order to save time, I'll just skip this, but it's just how that $11 billion is being, and the $2 billion for the Department of Defense is being spread out over several years. And finally, I want to talk about workforce, because this is very important. They've set aside $200 million just to the National Science Foundation to expand educational programs, meaning educational programs at universities, but also community colleges, because of the workforce needs of the semiconductor industry, which I would say are roughly split between engineering type of jobs and technician type of jobs in terms of workforce needs. And so they're going to establish a sort of microelectronics hub distributed across the US that's going to provide incentives for students to go into the semiconductor and microelectronics areas in terms of what I would expect to see in the future are scholarships to fellowships, abilities to do internships with companies, especially get hands-on experience. So there's a number of exciting things that are going to come out that are directly going to impact students and provide incentives for students to go into the semiconductor microelectronics fields. This is just some statistics, and that is that right now the semiconductor industry roughly employs about 300,000 workers. 50% have college degrees, so engineering degrees primarily. 25% have a graduate degree, and 20% are sort of high school and high school diploma, and maybe two-year programs. In any case, we don't graduate enough students to meet the industry demand for this, especially with the expected investment of the CHIPS Act. And so over the next 5 years, we're going to have to almost double the output of the US higher education system for industry, which means we're going to have to double the number of students that are graduating in microelectronics and semiconductor fields. So that's an enormous change. If you think about the number of students in your classes that we're going to double that in 5 years, which is pretty ambitious. This just shows sort of the pipeline of how that, you come to that number, and there's 325,000 roughly people employed in the semiconductor industry. There's some that leave, there's some that are retained, there's some that are entering, but in order to reach 600K jobs, which is what the ambitious goal of the CHIPS Act is to reach by 2030, there's going to have to be 165,000 new jobs created. And so again, this presents a big opportunity for students entering into microelectronics related fields. Some of the problems that we've had in terms of the semiconductor industry, before I turn this over to Russ, I just want to say is that a lot of the jobs and the understanding of jobs in the microelectronics industry are largely invisible to students and to the public. And in terms of the universities, there's an aging infrastructure, and people, faculty leaving, retiring and so forth, and we need to sort of invest in the infrastructure in universities to be able to teach semiconductor programs, which is expensive because, if you think about maintaining a clean room, it's an expensive proposition. And this is why there needs to be a partnership with industry. There are, industry needs to cooperate more with higher ed in terms of what the outcomes they want are. We need to update the microelectronics curricula, and we need to make sure that we're attracting more and diverse students into this pipeline, and in order to tap into the talent that is available in the US. And so I think I'm going to, since I'm running out of time, I'm just going to quickly say these are sort of the knowledge bases and the skill sets that are needed for this, and I can make these slides available to you if you want. Another plan is for that part of the training for students in the future will be that we'll provide opportunities for them to work at industry or at hubs, local regional hubs, in which there are manufacturing facilities that can be used for training students. And so there'll be a lot more access in the future for students to be able to get hands-on training in the skills that are necessary for the microelectronics industry. And I just want to say that I've been involved with this planning for microelectronics education future with some of my colleagues at other universities where we all have major semiconductor programs. And, we're, looking forward to an exciting future in terms of the growth of this industry and trying to attract students like you that are participating in this tech workshop and hope to make a case that this is an exciting future in terms of the growth of the industry and the growth of jobs in this industry. Thank you.
There we go. Thank you, Dr. Goodnick. That was a fantastic introduction to the CHIPS Act. I am Russ Harrison. I'm the Managing Director of IEEE USA in Washington, D.C. I'm also currently the Director of Government Relations for IEEE USA. So IEEE played a direct role in getting the CHIPS Act passed. It was often kind of quiet in the background, but we were here on the ground in DC working with legislators to craft the bill and to get it passed. And we're kind of proud of the work we did there. But what I want to emphasize is not just what the CHIPS Act is, as Dr. Goodnick did a great job of summarizing for you, but talk about the other parts of it, the non-CHIPS parts of the CHIPS Act, because the CHIPS Act is actually two different bills that were smushed together. The CHIPS Act, which invests, as you heard, billions of dollars in computer chip manufacturing in the United States. And then the other half, it's technically the CHIPS and Science Act. And the Science Act is arguably least important to America's long-term prosperity and to the workforce that all of you are going to move into. So we heard about the $56 billion for chips. Dr. Goodnick talked about a piece of that. There's kind of that 56 in tax incentives and other inducements to get companies to open fabs in the United States. Excuse me. But the bill is bigger than that. It also does research, regional technology hubs, technology transfer, STEM education, blah, blah, lots and lots of other things designed to not just change where computer chips are manufactured, but to fundamentally change how the United States innovates. And this is kind of exciting. Normally, when you get a big bill moving through Congress, like the CHIPS Act, you end up with a little kernel of whatever the bill's about, and then a bunch of other kind of random legislative proposals attached to it. The CHIPS Act really wasn't that. When Congress moved the CHIPS Act, they had a very clear idea of two things they wanted to accomplish. They wanted the United States to regain the production capability that we used to have to produce computer chips, but they also wanted to make some fundamental change to the innovation ecosystem in the United States, creating more brilliant ideas at universities and other places, and then pulling those ideas out of the university into American society to make us just a more innovative place all over the country. And that is very cool. It's also worth pointing out that the American CHIPS Act is just one of several CHIPS Acts around the world. Europe just passed a similar bill. Taiwan had a similar type program. Korea has a similar type program. There's a lot of these bills popping up around the world for the same purpose. The interaction of those bills is an entirely different session. We'll focus just on the US one because a lot of the countries are trying to do similar things. So within the United States, the non-CHIPS portion of CHIPS is focused on the National Science Foundation. NSF is one of the larger research agencies within the US government. NSF doesn't actually do research. It gives research grants to universities to do research for them. CHIPS created a new directorate within the NSF called the TIP Directorate, Technology, Innovation, and Partnerships. And within that are, as you see on the screen, a slew of new programs, some old programs that got moved around, that are designed to help US innovators, well, do what they do. To help universities create new ideas, and then to move those ideas into the private sector to create products, to create companies, to create entire new industries. The TIP Directorate is focused by law on exactly 10 research areas. There's a way to switch these out over time, but they're limited to 10, which is interesting. And you can see them up on the screen. They're all tech areas. In creating the TIP Directorate, Congress was making a very conscious and clear choice, saying that America's economic future is technology and technological innovation, and to some other stuff too. But tech is really at the heart of it. And so Congress is making a really big bet on you in this bill, that America's long-term future is dependent on you being able to do whatever it is you plan to do really, really well. One of the programs at NSF, and just to give you an example, are regional innovation engines. Now, I'm highlighting this because this really encapsulates what Congress is trying to do with the CHIPS Act. A regional innovation engine is kind of what it sounds like. It's a regional consortium of interests that come together to create new businesses, new investment opportunities, new innovation opportunities in a given part of the country, a given region. Here's the key. These regional innovation engines are supposed to be targeting the 10 TIP technology areas. In other words, they're supposed to be tech engines. And by law, they are supposed to be located in places in the United States that don't do a lot of innovating. So these aren't going into Silicon Valley, Boston, or Austin. They're going into everywhere else. And that is very exciting. What Congress did here is they said, we believe there are innovative people, innovative ideas, and innovative companies everywhere. But the way our current ecosystem works, almost all of the investments are going into just a few little places in the country. What if we found a way to do it everywhere? Silicon Valley is important, Boston is important, Austin is important. But there are other great people and great ideas in other places. What if we can create an ecosystem that provides them the support they need to succeed as well, creating rather than pockets of innovation, but rather one national innovative ecosystem that covers the entire country and the entire population? And Dr. Goodnick hinted at this in his, well, he said it actually in his presentation, which is when we're talking about investments in the chips industry, you need a lot of PhD engineers, you need a lot of people with master's degrees, a lot of people with bachelor's degrees, and a lot of people that don't necessarily need any of those, but who do need specialized training. Regional innovation engines will pull together universities, community colleges, local government, small business, state government to a plan to invest in a given area. And it has to include all of those and has to include all segments of the population. Which brings us to EPSCoR, another example of the things that the CHIPS Act is investing in. Now, EPSCoR is not a new program. It's actually been around for a while. There was a realization about 10 years ago that federal research grants to do research were doing great work, doing fantastic work, investing in the country and investing in jobs and students. But a lot of those research grants were going to universities in just a few places, the West Coast, the Northeast, Texas and a few other places. But they were concentrated in relatively few number of universities, which were concentrated in certain parts of the country. EPSCoR was created for everybody else. EPSCoR programs, this is an NSF program, are located in states, which are highlighted on your screen, that are not receiving their proportionate share of federal research grants. And EPSCoR has a carve-out where NSF has to spend about 12% of their budget in these states, which means we have research grants going to parts of the country that aren't doing a lot of basic research already to find the programs, to found the programs, found the companies in these states that are in fact innovating and make sure they get access to the resources they need. Again, the idea here, which is very conscious and deliberate, is innovation is not going to happen in a couple places in the United States. It is going to happen everywhere. And this is pretty exciting because the reality is there are innovative companies and there are innovative schools and there are innovative students and there are innovative professors everywhere. But because of the way the federal system was set up, it was very hard for a lot of these folks to access the federal investments that were available. EPSCoR exists to fix that. And in the CHIPS Act, EPSCoR's budget was dramatically increased, and it was given a more direct and more prominent role in finding innovative opportunities in all of these states. So there are some very conscious policy changes in CHIPS. There's the big ticket money items, which is very important to get fabs and to get production into the United States. But the policy changes that are underneath of those big dollar amounts are arguably even more important. We have broad regional innovation all across the country. Any part of the country that thinks we are not going to be Silicon Valley, but we can get into this game. We have ideas. We have talented people. We can do this too, should be able to access federal investments to give it a shot. We have deep workforce development across all sectors of the economy, all sectors of the American population. We have investments in K through 12 basic education, high school education, middle school education, but also apprenticeship programs, technical training, certificate programs, undergraduate, master's, and graduate education to reach out to the entire American public. explicitly in some cases reaching out to populations that have not traditionally participated in our innovative economy. The CHIPS Act deliberately and explicitly requires partnerships across fields, across sectors of the economy, and across regions. So it's not enough for a university to say, our university is doing research in quantum computing, that's what we're going to do. That program has to reach out to local small businesses, local workforce development programs, the local government, the state government, to get everybody on board to make sure the great quantum innovations that are coming out of that little university program are pulled out of the university into the broader economy, which is very exciting, to create, as I said, a true national innovative ecosystem. Politically, what the CHIPS Act has done is shift the focus of federal research policy away from kind of, we're just going to research everything. And we're going to look at really basic research, which is very important and still needs to be invested in, to say, we're going to do the big picture basic research, and then we're also going to do technology. And I think that potentially is going to be quite significant in the next couple of years. So what did the CHIPS Act do? In addition to investing huge amounts of money and finding ways to pull private money in to the chips manufacturing business, CHIPS created a bureaucratic infrastructure, and I mean that in a good way, a bureaucratic infrastructure to support all of those efforts, created the agencies, the bureaus, the pieces of the government that are necessary to connect all the pieces and make this work. It hasn't actually funded it all yet. More on that in a minute. The policy changes I mentioned a minute ago are done. They are in the CHIPS Act. The problem is the 56 billion, 31 billion that Dr. Goodnick mentioned is done. It was appropriated, it is locked in, it is going to be spent. Money for the workforce development, for the education, for the tech transfer, for the regional innovation hubs has not. It was funded for 2023, but it is not funded for 2024. So it's not guaranteed, which means we have to go back and keep getting it. There is, in fact, broad bipartisan support in Washington, D.C. and many other countries for technology research. But the United States is running right now a $1.5 trillion budget deficit. It's going to be $2 trillion next year if we don't change anything. And at some point, you just can't do that anymore. As budgets get tight, as Congress looks to cut back on federal spending, research is a really great place to look, because the federal government could end all research spending for 2024 without it actually having any impact on the US economy in 2024. Now, eliminating all research funding will be disastrous for the country in 2034, but Congress doesn't tend to think that far ahead. By creating the TIP Directorate, Congress has focused attention on specifically technology research, which ought to make it easier for us to defend our budgets in a tight budget environment and make sure the CHIPS commitments to broad workforce and broad innovation are in fact met. IEEE USA is in Washington, D.C., trying to make sure that happen. And we're working closely with IEEE members all across the country to make sure Congress understands what's going on, the promise of innovation, the promise of technology, not just to Silicon Valley, Boston, and Austin, but to every person across the country. I'm Russ Harrison, Managing Director of IEEE USA in Washington, D.C. There's my email address. I look forward to working with all of you on this and look forward to hearing all of you in the comment section. If you have comments, please feel free to put them in. Oh, we already got a couple good ones in there already.
Yeah, we do.
That, I believe
wow,
Nancy
this
is
has been
rejoining
amazing,
us
right?
to lead us in a conversation.
Yeah, amazing conversation. So we pushed some over there for you.
Oh, where do we start?
And while Nancy and Dr. Goodnick are connecting, I'm going to respond to Joshua's comments.
Okay.
CHIPS Act directly applying to manufacturing of semiconductors, support for tangential industries. The answer is yes. The CHIPS Act, the big picture headline CHIPS Act funding, the $56 billion, is targeted at semiconductors, but that's only about half the bill. The rest of the bill is really about innovation. There is funding for the semiconductor industry itself is broadly defined. And so packaging, for example, has a carve out in that section for unique funding. But even beyond that, the rest of the bill should be for innovative industries, even if they have nothing to do with semiconductors. I should also say there are a couple other bills. The Inflation Reduction Act that passed last year has a bunch of other money for other technologies as well. So yeah, Joshua, there's a lot of new federal money for a lot of different things out there.
So I guess Jordan had a couple of questions. I can maybe take an initial shot at that.
Nancy, did you want to take back over, or do you want me to just keep going?
No, keep going.
Okay. Yeah, so Jordan has asked a very interesting and disturbing question, which is, we have an American CHIPS Act that's designed to promote manufacturing in the United States. There is a European CHIPS Act designed to promote manufacturing in Europe. There's a similar program in Taiwan, a similar program in Korea. Other countries are looking at the same thing. China has its own programs. How's all this supposed to work together? And the answer is, we're not quite sure. And it is, in fact, something that the collective global technology profession needs to worry about. The technology world is global. We all benefit because it's global. Unfortunately, the supply chain challenges, as Dr. Goodnick mentioned a moment ago, highlighted some of the dangers of a global supply chain. And I think some politicians reacted perhaps too much to that. But we, the technology community, are going to have to work hard to make sure that the global ties and global cooperation that lead to, our current level of success continue in the face of politicians who have a natural tendency to be much more parochial. I think, Jordan, you have identified a real challenge for us in your question.
I think this is a similar question or comment.
Dr. Goodnick, did you want to take that, or do you want me to jump in?
Can you hear me? Because I'm not sure I'm...
Yes, I can hear you.
Oh, okay. No, I think this is just related to it's a follow-on to Jordan's initial question, which is, yes, I think one of the motivations for the CHIPS Act was a security issue, and that was ensuring the security of our source of semiconductor chips, and having a domestic source of those. I think it's actually part of the reason TSMC has actually opened a facility here in the U.S. I think that helps to mitigate some of the security issues of supply chain that we faced during COVID, and also in the future in terms of the changing political situation in the world. So as far as how do we maintain our relationship with our partners that we have, I don't see that as diminishing. I mean, I think we will still be having manufacturing diversified around the world. It could be that it shifts. For example, there have been interesting discussions in terms of the CHIPS Act semiconductors in Mexico, for example, and Canada, and what's called nearshoring of many of the supply chain associated with the microelectronics industry, and that is having it closer, spatially, is a way of ensuring more secure supply chains as well. And so I think we'll see an evolving ecosystem worldwide in terms of the microelectronics industry, but I think probably this is just a rebalancing.
Well, this has been an amazing discussion. I mean, I know it's a huge topic. So, Dr. Goodnick, thank you so much. I mean, it's so much compacted, so much information in a very short amount of time. And Russ, always a fan favorite at EduCap. You always give us some great insight to what's going on, not only in Washington, D.C., but how it's impacting everyone out there, in the trenches as we're trying to make all this really work. in terms of the legislation, the money, the regulations, and then the opportunities. So I think IEEE USA has a lot of resources on this. So I would counsel people to go there for some more information about the CHIPS Act. We'll go ahead and make these slides available through HKN. This session will be available on demand, and we'll make sure we get it out there because I think this is such a great call to action for so many different people, for our universities, for our industry, for our communities, for students, for everyone who's going to be impacted, which is just essentially all of us, which is interesting because it leads us to, we have our recruitment fair coming up next in terms of what's happening here at TechX. So great, go over there and talk to some recruiters about some of these opportunities, and we'll make sure we keep talking about this, keep pushing this information out in a meaningful way so that you can figure out how we can all be involved with the opportunities and the solutions that we need to have to advance our technology, our world, and the benefit of humanity. So thank you so much, Dr. Goodnick, for joining us, and
Yes.
Russ Harrison. Always a pleasure. TechX continues with a couple of sessions more this afternoon, like I said, a recruitment fair. And tomorrow we have a full day, including mega trends and other great conversations that continue these amazing discussions. HKN is the Honor Society of IEEE Etiquette at IEEE, and we invite you to find out more at hkn.org. Thank you.
Thanks, Nancy.